Hello everyone. We are Sativum. I am Sim Parmar and my partners are Harsh Patel and Anton Palazzo. Our project was to deflavor pea protein by the method of ozonation. Overview, what we're going to do in this presentation is we'll go through the introduction, the ideation, the alternate processes that we had before we settled for the one process we went forward with, the functionality testing to see if our project is even viable, the process description, process control, the economic analysis, the safety analysis, then we'll conclude the presentation, then we'll give the recommendations on the presentation, the acknowledgements, and the references. So the background of the project, Sativum was founded in 2020 by Harsh Patel, Anton Palazza, and Sim Parmar. Our aim was to ozonate pea protein to deflavor it using only dry processes because this was requested by our client that the process be dry. This was accomplished by designing a process that incorporated ozone safely in a controlled setting. The project was completed with input from the client who wants to stay anonymous and our consultants, Dr. Sultan and Dr. Zhang. Our clients did not require an economic analysis or any equipment sizing, but it was performed to give a better overview of the project. And we picked a production capacity of 5,000 metric tons a year to perform those analyses. The scope of the project. So what's in scope is we conduct the protein functionality testing with the research experimentation. We found the operating cost and project cost estimation, a detailed PFD and PNID, handling of waste and its byproducts, process safety analysis. What we were not supposed to do was the equipment sizing, the detailed economic analysis, as we have done the economic analysis, but to a lesser degree and not very intensive. And we did not produce our own pea protein. The pea protein was supplied by AGT Foods.
Starting with the ideation of the design process, we looked into three different parts. That was the oxidizer we are using, the reaction vessel, the separation unit. For our oxidizer, we decided that the ozone would be a great oxidizer. We found that the ozone has been getting traction in the research and implementation in the food process industry. Ozone is known as a disinfectant in water treatment. It has been used in sanitation of food contact equipment and surfaces. It has also been used in the treatment of fruits and vegetables. In the ozone generation technology, there are two main processes that can produce ozone from dry air or pure oxygen. One is the photochemical reaction due to UV light, and another is through corona discharge between dielectric plates. For our process, we chose the corona discharge process due to its commercial availability. Next is the reaction vessel. The main option we have is using a fluidized bed as we can get lots of mixing and it's also known for good heat transfer. So we looked at what the physical properties our pea protein have for fluidization. Our protein sample have 420 to 450 kilograms per meter cube bulk density and have an average particle diameter of 72 microns. From those values, we compared it to the Gildert classification chart and found that our pea protein is within Group A or Group C classification. From that, we decided that the pea protein could have cohesive properties, which can increase the fluidization velocity needed for these solids. So we looked into vibratory fluidized beds, and we found that they can reduce the agglomeration that could happen, lowering the complete fluidization velocity. So with that, we moved with our initial alternative processes. The first alternative we have is the Hopper feeder cyclone process, where the pea protein is fed to a PFR of flowing ozone into the cyclone, where it can mix some more. So this was ineffective as the pipe doesn't create enough turbulence for mixing. The second alternative we have is using a fluidized bed to suspend the pea protein to pneumatic transport and into a collector bin. The last alternative we have is, like the previous, using the fluidized bed for suspension of pea protein, but we added a cyclone so that we can separate the exhaust gas with the pea protein to stop ozonation. So using a decision matrix, we came to the fluidization bed reactor with a cyclone to be the best to design. Before we fully developed the process, we looked into some functionality testing. The solubility of our pea protein is less soluble than whey protein. The texture is soft and smooth. It gets sticky when wet, and it behaves like talcum powder when exposed to wind. When tasted, it's very grassy and it's like hay or leaves. What we tested next was the fluidization of the pea protein. So we performed the experiment in the undergrad lab with the supervision of Majak Mapur. We found that the pea protein was very cohesive as it clumps up the bottom and it sticks to the wall. So from the collected data of the bed pressure and superficial velocity, we found that the agglomeration caused the fluidization velocity for the whole bed to increase, as shown in the graph there. We also have developed an experiment procedure to test the reaction between ozone and pea protein, but we were unable to do the experiment due to restrictions on COVID-19 in the lab spaces we require. So from the literature, we came to these conclusions. That the grassy flavor of pea protein is associated with aldehyde molecules. We also found that ozone increases the degradation of hexane, which has a similar oxidation property to hexanol. This means that the grassy taste can be reduced. We also found that ozone rapidly decomposes to oxygen and it leaves no residue. And we also found that ozone treatment in wheat flour also resulted in decrease in solubility and loss of color.
So this is the process that we were able to come up with um, after much meetings with the consultant and the client. As you can see, we took a lot of our alternative design and we combined it together to get this overall process. So this starts by having a gas feed of air that is a dry filtered air feed that goes into the ozone generator at ambient conditions. The oxygen is then converted to ozone by corona discharge, as Anton mentioned earlier. The ozone concentration is determined by the amount of oxygen in the airstream and the ozone generator settings. This then goes to the blower, which creates a pressure difference, moving the air from the ozone generator, or the ozone from the ozone generator, to the fluidized bed reactor. The flow rate in this is determined by the blower settings. The air fractionated pea protein is loaded into a closed bin screw auger hopper feeder, and the screw auger is powered by 10 kilowatts electric motor, which controls the speed of the auger feed into the fluidized bed. The pea protein and ozone react inside the chamber as fluidization occurs, which causes some small particles to experience pneumatic transport and exit with the exhaust gas. The ozonated pea protein exits through the spout at the opposite end of the bed, and the recycle stream is reintegrated into the bottom of the fluidized bed. Here's the component that includes our separator, which is a cyclone. And in this, the exhaust gas from the fluidized bed enters a cyclone, and the pea protein particulates get separated from the gas and enter a collection bin, which is the underflow. And the overflow gets recycled back into the fluidized bed. This not only helps us to reuse or use up more of the ozone in the system, but it also lets the ozone decompose, gives it ample time before being released into the environment or into whatever afterwards. So we designed a basic process control and instrumentation diagram, and the main components we came up with that were absolutely necessary for this process were a flow rate indicator before the fluidized bed where the ozone is being fed. Within the fluidized bed, we need a pressure and temperature indicator just to make sure that the conditions are actually ambient at 1 atmosphere and room temperature. The flow rate exiting the fluidized bed reactor into the cyclone will be monitored with an indicator as well. And finally, with the fluidized bed reactor, we'll also have a flow rate indicator that's monitoring the spout where the pea protein and ozone are going directly into the product collector bin. For the exhaust gas that is exiting the bin, we also have a flow rate indicator, which has a high flow rate alarm just in case conditions get there's too much ozone being released into the environment. Mostly the operators for this process will, as you can see, everything is an indicator, so they'll need to be monitoring everything themselves and making changes accordingly for this design. Here are all the instruments and types and descriptions that I just mentioned.
So here is the economic analysis for this project. As we see that pea protein is a big demand. It's in big demand, so this has room for a lot of growth. As we see in that graph, it seems like the market is only going to grow until 2028, according to this, and it's valued at 214 million in 2020, and it's going to keep growing at a rate of 14.7 over that forecast period until 2028. Even though pea protein has such a high demand, the consumption is really low just due to the fact that people can't eat it. It does not taste really good. But that is where we come in, and we have solved that issue of flavor as our project takes out that grassy beanie flavor from the pea protein and makes it consumable. So cash flow, the initial startup costs, which will include all the equipment costs and all of that stuff to start up the process, it's roughly 4.8 million USD. The annual expense that we calculated came down to 12.3 million USD a year, but our annual sales will be 20 million USD a year. That means we'll have a profit of over 7 million every year. We will be buying the pea protein at the rate of 2.2 USD per kilogram, but we'll be selling it at $4 USD. Sativum came at that price together as we noticed that that's the price that will be able to keep up with competition while also covering all our expenses and giving us sizable profits. The price of 2.2 USD was provided to us by AGT Foods.
So in order to complete the design of this process, we were, after we had created it, we looked at some of the safety components that would have to go into it. So first thing we looked at were the safety data sheets for ozone and the pea protein specification sheet that was provided with the sample pea protein from AGT. Upon analyzing these, we determined there to be a need for a walk-in fume hood, and there could be a potentiality of ozone toxicity through exposure for any operators or bystanders. For the unit itself, we did a HAZOP study on it, and we looked at the deviations for things such as pressure, temperature, composition, and we kind of sought out the consequences that would result due to those deviations and how we could mitigate those. With the possibility of dust explosions, we recognized that there'd be an electrical classification from the National Electrical Code, and we determined this to be Class 2, Division 2, Group G from Article 500. Our environmental analysis and our study and research into ozone and all the effects of ozone determined that we would need to recommend the need for a wet scrubber system or an ozone destroyer system to minimize the ozone emission into the atmosphere. To further on that, for ozone release, we did a ozone lethal concentration calculation where we determined 30 ppm per second of ozone will be released. This is, of course, much greater than the lethal amount of 0.1 to, or sorry, 5 ppm. And this kind of made us recommend the need for a destroyer system as well as a wet scrubber system, as ozone has a half-life of 20 to 50 minutes in air or 20 minutes in water. So we believe that the wet scrubber system would work very well. The federal regulations, we researched and we found out that this was 63 parts per billion over an 8-hour period. So assuming we make this 30 parts per million per second, that would need to be conformed to. However, it's to be noted that the 30 parts per million per second would only be created if there is absolutely no reaction taking place, and this is the absolute worst case scenario, which we do not expect to happen.
So, to conclude the presentation, the undesirable grassy flavors of the pea protein are associated with the aldehyde molecules, mainly hexanol. The pea protein powder is cohesive and is represented by Geldart Class C classification, requiring the need for agitators such as a vibratory system. Ozone rapidly decomposes to molecular oxygen with a half-life of 20 to 50 minutes. It does not leave any residue and it can be generated on site. Process releases aerated fine particles which could lead to dust explosions. The area in which this process is taking place should be electrically classified and labeled as Article 500, Class 2, Division 2, Group G of the National Electrical Code. High safety precautions are required in ozone handling as it can be lethal at concentrations between 0.1 to 5 ppm, which is parts per million, as outlined by Harsh. Sativum's annual revenue is greater than its annual expenses, as described by me earlier in the economic analysis. This is a very in-demand product that's going to make a lot of money, and our profit would be 7.1 million a year in American dollars. Our recommendations for this project, for this process are: the ozonation treatment needs to be performed to provide a clearer picture of the project feasibility, as we were unable to do so ourselves due to COVID-19. The testing for concentration of ozone gas in the exhaust gas stream should incorporate a feedback loop that ceases operation of all process vessels in the event of high ozone release. High-frequency pulsating air streams should be useful in dealing with agglomerations of the pea protein. Due to a potentially lethal output of ozone in the worst-case scenario from the exhaust gas stream, 30 parts per million per second, Sativum recommends an ozone destroyer system be instated to convert the exhaust ozone to oxygen prior to atmospheric release to meet federal emission regulations of 63 parts per billion over an 8-hour period. And more in-depth economic analysis should be performed to better understand the market and all its flow streams, as we did a brief economic analysis, not in depth, because our client did not require it. And inflation should have also been considered in a better, accurate costing, which we did not do either. Our acknowledgements are our two consultants, Dr. Jafar Sultan, Dr. Leifeng Zhang, the AGT food supplier, Dr. Mohammed Tulbak, who provided us with a pea protein, and the coordinator who let us perform our fluidization experiment, Dr. Majik Mapior, and of course our client who would like to stay anonymous. These are references, and we thank you all for listening to us. Hope you enjoyed the presentation.